So now we can talk about surface area of revolution. So what if I took this region, right, and I revolved the graph around the x-axis, and I get something like, see if the auto circle tool will work with me. That's skewed a bit, but good enough for the illustration. That's fine. So if I take this, duplicate it, and put one over here, stretch that out, get that a little bit bigger, something like that. Yeah, that's good. So I'd have something like that, right? Sort of a funnelish thing. It's not a cylinder, it's not a cone. So the surface area is not so simple, right? Not the volume, we've done that, but the surface area. What if I had something that was simpler? Like if I had, let's do a small graph here. If I had something like this, okay? So if I had just a linear function like this, like that, and I wanted to make, if I wanted to revolve that around the x-axis, and the auto circle tool is not working with me. Okay, good enough. Let's duplicate that, put it over here, make it a little bit bigger. Right. So then I would get like a cone with the tip chopped off, right? This is called a frustum. Okay, let's say right here we have A, and here we have B is the end of the interval, right? Okay. Well, that's going to want to snap the way it snaps. Oh well. It's off a bit, whatever. I'm not going to worry about it. It's called a frustum, and then the lateral surface area of a frustum is basically given by, if we call this function, let's call it f, the lateral surface area of the frustum, this is given by pi times f of a plus f of b times this lateral, it's called the lateral height of the frustum, okay? We'll call that L, okay? This formula, the book actually goes through the derivation of this formula. You can look that up if you want to. It's not that it's difficult. It's you set up a proportion, use some geometry, there's some algebra. It's not difficult. It's just a little bit tedious. So you can look that up if you want to. But for now, let's just take this as that is the formula for the lateral surface area of a frustum. Okay. So if we had that, that'd be great. So what we're going to do is we're going to chop this up into pieces, into a bunch of frustums. I hope that's the right plural. Maybe it's frusty. I don't know. That would be hilarious if that was the actual pluralization. It's probably frustums, though. So what we're going to do is we're going to cut this interval into pieces, equal pieces. So let's say like this, here, here, here. Try to cut it into 6 equal pieces, or equal-ish. It's not perfect. We'll pretend that I did a good job cutting it into equal pieces. Whenever I'm drawing diagrams, I have to pretend sometimes. Okay, so something like that. So there are these points on the functions. There's f of a. Here's f of x1. Well, the ordered pair a comma f of a. Here's x1 comma f of x1, and so forth. Okay. And so for each of these, we can make a segment connecting those 2 points. So this is it starts out a lot like what we did with the surface area. The arc length, I mean to say. Okay. So probably this one is the one that's drawn the best. They're all off by a little bit, but let's say that this one is the best one. Okay, so let's call this xi and xi minus 1. It's the one with the best gap there. It's going to turn out to be the best diagram. So if I build a frustum out of this, I guess we'll make it in red. Okay, that's a pretty good circle. It's off kilter a little bit, but good enough. Okay, so one side's a little bit smaller than the other side. Not by a huge amount, but just a little bit. Okay, and I can connect those two here. Okay, so the length of this segment is delta x, and I won't label it right now because I don't want to clutter too much. And the length of this segment is L, which we're going to need. Okay, so the lateral surface area of that section, where do I want to put it? Let's put it here. The lateral, I guess I want to use a, no, let's switch to blue. Okay. The lateral surface area of that frustum, right, based on the formula that we talked about briefly up here, this is pi times f of x I minus 1 plus f of xi times L. Okay? L being the arc length section that we talked about previously. So this equals pi times f of xi minus 1 plus f of xi times the square root of 1 plus f prime of xi star. So again, I'm borrowing from the arc length discussion earlier. So that is the lateral surface area of that frustum. And if we add them all up, then we'll get all of them, right? So the lateral surface area estimate for the whole thing, right? Well, this is going to be the sum as I goes from 1 to n of pi times f of xi minus 1 plus f of xi times the square root of 1 plus f prime of xi star. Remember, xi star, this is a point in the interval guaranteed to have a slope equal to the slope of the red segment, right? Somewhere on this graph, there's a point that has the same slope as the segment we labeled L, okay? From the discussion earlier. That squared delta x, okay? So there's our estimate. And, you just increase n to whatever number you want, and you'll get your estimate. And if you want a better estimate, use more frustums, right? Increase n. Before we talk about the limit, there's something that we have to address. So this is a little bit of a problem that we have to evaluate the function at two places. Really, three places. So we have 3 x coordinates involved here. We kind of need to reduce that. And if for nothing else, out of convenience for the formula we're going to develop, I want to combine these two into a single value, basically. Since our function's continuous, right, we have a continuous function on our interval, then because of the intermediate value theorem, so by the intermediate value theorem, there has to be some x coordinate in the interval where the function value there is equal to the average of the two values at the endpoints of the subinterval. So there is some, we're going to run out of room here. No, okay, we got room. There is some xi double star, so it's another x coordinate that's guaranteed to be somewhere in the interval, xi minus 1 comma xi, such that f of xi star star equals f of xi minus 1 plus f of xi all over 2, right? The function value will be the average of those two at the endpoints, okay? That's guaranteed. So if I multiply by 2 on both sides here, I can get rid of those 2's, and I can replace this guy here with 2 times f of xi star star, or double star, maybe I should say. So this equals the sum as I goes from 1 to n of pi times 2f of x I double star. And then, of course, times the square root 1 plus f prime of xi star squared delta x. Okay? So again, that's our estimate, right? So the actual value, the surface area that we're looking for, this will be the limit as n goes to infinity, the number of frustums goes to infinity, of the sum as I goes from 1 to n of 2 pi, so I'm switching the order here, but that's just window dressing, of f of xi star star times the square root of 1 plus f prime of xi star squared delta x, right? There you go. That is the exact surface area. Now, we are obviously not going to go through this every time we want to calculate a surface area. We're going to get a formula out of this. And you might notice, this looks an awful lot like what we did with the arc length, where we had a limit of a sum of something multiplied with delta x. The number of objects is going to infinity. Delta x is going to 0. This is an integral. This is a Riemann sum, right? The difficulty we have, though, is that I do not have a single x coordinate. I can't say, oh, this is just g of x, because there's two different x coordinates. So we're going to have to gloss over a detail. You can go look it up somewhere, find a calculus book that goes into more detail. And if you would like to do that, just ask me and I'll give you the right direction. If you want to major in math or get a minor in math and take real analysis, you can go through these details and really examine the nuts and bolts. But we're going to skip that here. This is only Cal 2. This is not, like a graduate level course. So basically, since delta x is going to 0, the thickness of our frustums is shrinking, right? This delta x here is going to 0. So the thickness of the frustum is going to 0. So the places to pick from delta x, the places to pick from xi star and xi star star, that's shrinking. Delta x is going to 0. And so, there's a little bit of error involved if you say, well, let's just say that xi star and xi star star are equal. Let's just pretend they're the same. There'd be some error in that. But if n is going to infinity and delta x is going to 0, they will be forced to be equal, right? They're being squeezed. So we'll say that we're going to treat these as though they are the same, even though they are not, because in the limit, they're forced to come together, okay? So those I don't want to say shortcomings, but those, this is what we call in mathematics hand waving. I'm just going to sort of like I'm a close-up magician, right? I'm tucking a card into my shirt sleeve. I'm just going to wave my hands and you don't notice, right? So let's say I'm waving my hands here. This equals the integral from a to b of 2 pi times f of x times the square root of 1 plus f prime of x squared dx. So this integral will give me the lateral surface area, or the surface area of revolution of the function being revolved around the x-axis, okay? So there's a couple things to point out. Notice that this is just the arc length integrand from before. This is sometimes called ds. S for arc length. You might remember that from pre-cal. So ds, this is equal to, there are two versions. So there's 1 plus dy dx squared dx. And that's also equal to the square root of 1 plus dy dx. Dx dy. Okay, dy. So if you want to, it is possible to switch this over to, say, y, switch this over to dx dy, this to dy, and then make sure you switch your limits of integration, you can sometimes switch over to integrating with respect to y if you want to. It's just you typically don't need to do that. So in particular, if you have some function x equals g of y, right? And you're on the interval from, say, c to, not a, so you're storing that c to d, and you're revolving around the y-axis, okay? You could go through this same formulation, go through all the same steps, and you would be able to say, oh, well, that surface area, that's going to be the integral from c to d of 2 pi g of y times the square root of 1 plus g prime of y squared dy, okay? And then still, if you really, really wanted to, you would be able to switch this into being an integral with respect to x if the conditions are right. Maybe we'll see an example of that later. Anyway, this is generally the formula that we're going to use most of the time, because we'll have functions typically that are y equals a function of x most of the time. Anyway, here's that entire thing all on one screen, just in case if you wanted to, just have a screenshot of the whole thing. So for our first example, let's do one that doesn't really need an integral, that we could just do geometrically. If you graph y equals 1/2 x, or at least a quick sketch of it. I'm not going to try to be too precise. We get something like that. Here's 4, here's 2, right? And if I try to make it, if I revolve this around the x-axis, I get a cone. So what's the height of that cone? 4. What's the radius? 2. And then you can look up the formula for the lateral surface area. I don't recall it offhand, but it's not that hard. Anyway, let's see. We don't know the formula. How do we calculate it? Well, I've got a y as a function of x revolving around the x-axis. So I'm going to use the integral from a to b of 2 pi y times ds. And the ds depends on with respect to which variable you want to integrate. Since we're revolving around the x-axis, it's probably going to be easier to integrate with respect to x. Sometimes either way will work, and sometimes one way does not work, and by default, I think you should attempt dx in the case of the x-axis. So this is going to be the surface area. This will be the integral from 0 to 4, that's our interval, of 2 pi times 1/2 x times the square root of 1 plus dy dx squared dx. Okay, so of course dy dx is 1/2, right? So if you square that, you have 1/4. So this is the integral from 0 to 4. The 2 and the 1/2 can go ahead and cancel. So this will be pi x times the square root of 1 plus 1/4 dx, right? 1 plus 1/4, that's 5/4. And then the pi as well is just a number that can move out front. So pi times the square root of 5/4 times the integral 0 to 4 of x dx. So I get pi times the square root of 5/4 times x squared over 2, evaluated at 0 and at 4. So I get pi times the square root of 5/4. Or if I want root 5/2, I guess I might as well do that. Times, well, 4 squared over 2 is 8. Minus 0. So I end up with pi times 4 root 5. Okay, and that is the lateral surface area. And if you want to go Google it and find the formula for the lateral surface area of a cone, you can check that this is correct. Okay, so I want to do another one for which we don't really need an integral. And this time we will check that this is correct. Take a look at the graph there. Well, the function, and think about the graph. Y equals the square root of 9 minus x squared. I won't graph that yet. We'll just move forward with the formula, and then we'll do the graph afterward. So I'm going to integrate with respect to x, because by default, if I'm revolving around the x-axis, then that's what I'll go with. There are exceptions, but that's the default you go for. So the surface area, this will be the integral from -3 to 3 of 2 pi times the square root of 9 minus x squared times the square root of 1 plus dy dx squared dx. Okay, so of course dy dx, this is equal to 1/2 times 9 minus x squared to the -1/2 power, that's the power rule for the outside function, times -2x, the derivative of the inside function because of the chain rule dx. So if I want, I could write this as a -x over the square root of 9 minus x squared dx. That would be the same thing. Okay. Oh, I have a mistake here. Why am I doing dx? I was thinking about substitution, right? That doesn't need to be there. My mistake. There's no dx. Sorry. This is not a substitution. It's just the derivative. We're going to do a substitution at some point later in a different example. So I was just kind of expecting that here. Okay. So if I square that, I'll have x squared over 9 minus x squared. So this equals the integral from -3 to 3 of 2 pi, which I guess I could move out in front. I'll do that at some point. Times 9 minus x, the square root of 9 minus x squared, times the square root of 1 plus x squared over 9 minus x squared dx. Okay, so this looks pretty bad, looks complicated, but don't worry too much. This is going to simplify quite a bit. So I'm going to notice that I can write this 1 as 9 minus x squared over 9 minus x squared. Okay, and I won't skip steps here. You might see what's coming next, but I'll go ahead and write it out. I probably could have moved the 2 pi, but that's okay. So 2 pi root 9 minus x squared times the square root of 9 minus x squared over 9 minus x squared plus x squared over 9 minus x squared dx. And of course, now that I have a common denominator, I can combine these. 9 minus x squared plus x squared is, of course, just 9. So this is the integral from -3 to 3. Still not remembering to move that 2 pi. I guess maybe I'll do it in the next one. 9 minus x squared times the square root of 9 over 9 minus x squared. And some of you are probably seeing what's going to happen soon. So I'm going to use a property. I'll go ahead and move the 2 pi. I'm going to use a property of radicals, where if you have a radical of a quotient, you can apply the radical to the numerator and denominator separately. So root 9 minus x squared times 3 over root 9 minus x squared. Well, isn't that convenient? We get to do some cancellation. And that 3 can move out in front, so this is 6 pi times the integral from -3 to 3 of dx. Well, that cleaned up rather nicely. There's a lot of rearranging we had to do, but it simplified a whole lot. So this is 6 pi times x evaluated at -3 and 3. So this is 6 pi times 3 minus -3. So that's 6. So 36 pi. There we go. Nice clean number at the end. So let's backtrack a little bit and think about, what does the graph of that function look like? And I'm going to, well, give it away pretty quickly here. It's not quite centered. Let's do that. There, that's centered. This one won't be, but that's okay. So, why is he drawing a circle? Well, that's kind of the graph that we have. Basically, that was almost perfect. We'll call that just shy of perfect. That's the graph of y minus, I'm sorry, y equals the square root of 9 minus x squared. So here's 3, negative 3, 3. And if you revolve this around the x-axis, you get a sphere, right? If you remember the surface area formula for a sphere, it is 4 pi r squared. The radius is 3. This is 4 pi 3 squared. We get 36 pi. So you can say, well, why do we bother with all that? Well, I could ask you, why is this the formula? How do we know that? Where does that come from, right? So obviously that comes from geometry, but you could derive this through calculus as well. Not that you would have to, but you could. Okay, so now let's do something that we can't really do so easily just with geometry. This is really the why. Why would we care to do this? So I'll start by drawing my circle out as close as I can. Oh, and in fact, what I ought to do, because I think this will snap to, well, maybe not. Is that perfect? I don't know. Let's call that perfect enough. Let's call that close. Okay. So again, the radius is 3 in this example. I'm going to clean this up a little bit. Radius is 3. But we're not integrating from negative 3 to 3, just 0 to 1. So on my graph here, here's 2, here's 1. I'm taking just... Oh, and I probably should get rid of the bottom, shouldn't I? We'll pretend I erased that perfectly so that it lines up real nice. Okay, so we're taking just this segment here and revolving that. So I'm making basically this, and this auto circle is off kilter a little bit, but we'll call that good enough. Basically, I'm making, oh, you know what, yeah, they'll call that, I think, close enough. Yeah, we'll call that, okay, good, right there. Okay, the surface area of just that slice. So it's like a ring, kind of like when we were doing the shell method before. It's a little bit like that, in that it's like a ring shape, but it has no thickness. It's not a volume. It's a surface area. So I'm going to try to highlight the back in sort of a medium blue, and I'll highlight the front in a lighter color. Okay, and then the front we'll do in this color. Well, it's not that much lighter, it's brighter, I guess. Whatever, you get the idea. So this, how do we do this with geometry? Do you have a formula for a section of a sphere? I imagine there probably is one, but where did the formula come from? Did someone work it out with calculus? Maybe. So all we gotta do is do that same integral, but integrate 0 to 1 instead of negative 3 to 3. So I'm gonna go through the whole thing again. I'm not gonna just go borrow the same, the result. Although we could, just interest of time we could, but let's go ahead and go through it. It wouldn't hurt, I guess, to see the steps again. So the surface area, this will be the integral from 0 to 1 of 2 pi times the square root of 9 minus x squared times the square root of, I guess this I will borrow, 1 plus x squared over 9 minus x squared. That's the result of a little bit of finding the dy dx, squaring it. So I'm reusing that from the previous example. So then this equals integral from 0 to 1. The 2 pi is still going to, I guess it's going to stay inside for a long time again. The auto circle tool on a little delay there. Okay. So this is 9 minus x squared times the square root of 9 minus x squared over 9 minus x squared plus x squared over 9 minus x squared dx. So this equals, I guess I'll move the 2 pi now, integral 0 to 1 square root 9 minus x squared times the square root of 9 over, well, I guess it didn't need to be that big, did it? 9 over 9 minus x squared dx. So this equals 2 pi integral 0 to 1 root 9 minus x squared times 3 over the square root of 9 minus x squared dx. We get some cancellation. If I can make an x that looks like an x. There we go. And so I get 2 pi times integral 0 to 1 dx. This is 2 pi times x evaluated at 0 and at 1. So 1 minus 0. So 2 pi. So 2 pi is that surface area of that section of a sphere. So what you could do is you could say, well, I could probably make a formula based on the interval from a to b, right? It would be 2 pi. What would that be? 2 pi times b minus a, essentially, right? If you wanted to do that, and that would be the surface area of a section of a circle based on any interval, if you wanted. Okay, so let's do one for which there really is no geometry we could use. We really have to use an integral. So I'll do a kind of a rough sketch of y equals the cube root of x. I'll try to make it accurate. Yeah, that's okay. A little lumpy, but okay. So yeah, that's okay. There's, it may be a little bit hard to tell from the way I drew it, but there's a vertical tangent line there. The slope is undefined. In other words, the derivative is undefined there. So I'm going to move that off to the side a little bit, maybe even shrink it down so it fits. Well, I guess I don't need to shrink it down. That's fine. Just like that. Okay, so we are revolving about the y-axis. So you know what, in fact, roughly from like here to here, we're revolving this section. Okay. So we are making something like this. I guess I will just duplicate this one. So something, well, there we go. Something like this. Something like that. That surface area. It's skewed a bit. I'm not going to worry. That's skewed a lot, actually. Anyway, I'm not going to worry about it too much. But that shape, you get the idea. So I'm going to want to do the integral from, well, 1 to 2. Let's be my surface area of 2 pi x ds. Okay. Now, which ds do I use? Do I want to do the differential with respect to x or with respect to y? Well, since I'm integrating with respect to, since I'm revolving around the y-axis, I probably should do dy. It turns out with this example, you actually could do dy or dx. So we'll do both, but I'll do dy first. Okay. So this is the integral from 1 to 2 pi y cubed, right? If we solve for x, we get y cubed, right? Okay, times the square root of 1 plus dx dy squared dy. So dx dy, that will be 3y, not to the fourth squared. Okay, so this is integral. In fact, let's move that 2 pi right now. 2 pi integral from 1 to 2 y cubed times the square root of 1 plus this guy squared, so 9y to the fourth. I think my brain was anticipating the 4 at this stage. So there we get a not very difficult integral. You might recognize that the derivative of the inside, the radicand, the derivative of the radicand is y cubed. So that's convenient. We have a y cubed right here. So let's use that. Let's say I've been writing this very large, and I want to do both approaches. So I'm going to shrink this down a bit. Yeah, and I want to leave all this space empty to do the other approach. So let's do u equals 1 plus 9 y to the fourth. So then du equals 36y cubed dy. Okay. So I'll have 2 pi over 36, because I need to borrow the 36. Integral from, well, if I plug in 1 into, well, you know what? I'm not switching yet, so it's still 1 to 2 times the square root of 1 plus 9y to the fourth times 36y cubed dy. Okay, so then I can switch over. So I'll have pi over 18 times the integral. My new bottom limit of integration is going to be 10. And my top limit of integration, 2 to the fourth, is 16 times 9 is 144, so 145. Times u to the 1/2 power du. Okay, so then this is pi over 18 times 2/3 u to the 3/2 power, evaluated at 10 and at 145. So we get 18, pi over 18 times 2/3. You know what? Let's make that pi over 27 then. Pi over 27 times 145 to the 3/2 power minus 10 to the 3/2 power. And there we go. That's not a nice pretty number, but there we go. That is that's that surface area. Okay, and the integral was not very hard. It worked out fine. Now, what if I wanted to say, well, for whatever reason, I wanted to switch and do the other option, the other ds, right? I didn't want to use the dy version. I wanted to use the dx version. Well, here's how you do that. You probably shouldn't do that most of the time. Just do the one with respect to whatever your axis of revolution is. That's usually going to be the better way to do it. But what would happen if I switched? So the surface area, well, that's going to equal the integral. And since we're going to do with respect to dx instead, my integral is no longer 1 to 2. It's now 1 to 8. Okay. I have to do a change of variable since I'm using dx, not dy. So the 2 gets cubed to make 8. Okay. So of 2 pi x, very important. This does not change because this is the radius through which the revolution is occurring. It's an x coordinate, right? This piece of the graph here, its distance from the y-axis is an x coordinate, right? This is basically in the setup we did at the beginning of, the beginning of this video. This is f of xi star star, right? This is the radius of the revolution. So that does not change here. It's not like, oh, well, if I'm integrating with respect to x, then this changes to y. No, it does not. It's x because we are revolving around the y-axis, and changing to the other option for ds does not change that fact. Okay. So, I'm hitting undo. I mean to erase that. So, times, instead of this ds, the other ds. So, square root of 1 plus dy dx squared dx. And I'll tell you up front, this is going to be harder. This is a more difficult integral, but I wanted to show you, here's how it would go, here's what would happen. In particular, because what if you start the one that is going to be the more difficult one? At what point should you start thinking, this seems a little hard, maybe I should switch to the other one? So supposing you had started with this one, how would you know when it's getting really messy? So let's try this out and see what happens. And in fact, I might need to move this a little bit, because I'm kind of short on horizontal space, but I have enough vertical space. So let's do this. Yeah, let's do that. Okay. So, y is, cube root of x. I'll copy that over here. Y equals x to the 1/3 power. So dy dx, this is 1/3 x to the negative 2/3 power. Or in other words, if I want, 1/3 times x to the 2/3 power. Okay. So that means that I'm doing 2 pi times the integral from 1 to 8 of x times the square root of 1 plus this guy squared, 1/9 x to the 4/3 power dx. And maybe you can already see that this is maybe a little harder to deal with than this. It's got similar elements to it, but it's going to be more challenging. Okay, so I'm going to go ahead and try to combine this into one fraction. So this is 2 pi times the integral from 1 to 8 of x times the square root of 9 x to the 4/3 power over 9 x to the 4/3 power plus 1/9 x to the 4/3 power dx. So this is the integral, 2 pi times the integral from 1 to 8 of x times the square root of 9x to the 4/3 power plus 1 all over 9x to the 4/3 power dx. Okay. And at this point, you might start thinking, I don't know about this. This is getting to be a bit much. So 2 pi times the integral from 1 to 8 of x. And I'm going to use a property of radicals, where we have a radical of a quotient. You can apply the radical to the numerator and denominator separately. So this will be the square root of 9x to the 4/3 power plus 1 over 3x to the 2/3 power dx. And of course, this x here is like an x over 1. It's in a numerator, right? In fact, let's do that so it doesn't look like it's in a denominator. So what order do I want to do this in? Well, I'm going to move this 3 out front. So 2 pi over 3 times the integral from 1 to 8 of x to the 1/3 power times the square root of 9x to the 4/3 power plus 1 dx. You might wonder, wait, where's the 1/3 coming from? Well, basically I'm doing x divided by x to the 2/3 power. So x to the first power over x to the 2/3 power. And you subtract 1 minus 2/3 is 1/3. Okay. So you might think, like already this is, I mean, this has shifted down a little bit. It's, down the page a bit, but now this is more steps, isn't it? 1, 2, 3, 4, 5, 6 to be done. 1, 2, 3, 4, 5, 6 to not be done. So you might think this is not really working, but let's muscle through. Let's do the rest of it. So you might notice the derivative of x to the 4/3 power is 4/3 x to the 1/3 power. Hey, that's a multiple of this guy. So that's a substitution. So let's say that u equals 9x to the 4/3 power plus 1. So du equals 36, or no, that's 12. Yeah, 12. 12x to the 1/3 power dx. Is that right? Did I have 12? 9 times 4/3? Yeah, 12. Okay. So I'm going to group the x to the 1/3 with the dx, and I'll have to borrow a 12 from somewhere. So this is going to be pi over 18. Does that seem familiar? Times integral from 1 to 8 of the square root of 9x to the 4/3 power plus 1 times 12x to the 1/3 power dx. Okay. So now when I switch over to u, my bottom limit of integration will become 10. My top one, well, 8 to the 4/3 power, well, that's going to be cube root of a is 2 to the 4th power 16 times 9 is 144 plus 1 is 145. Maybe that sounds familiar or looks familiar. So this is pi over 18 times integral from 10 to 145 of u to the 1/2 power du. Where do I remember that from? Yeah, that's the same thing, right? So we're going to get the same answer. I'm not going to write the rest of it because it's the same. But you can see that one is quite a lot easier than the other. And I don't want to say that's always going to happen, but that they'll both work out just fine. This works in part because our function is a one-to-one function. It's invertible. So either one will work. I don't want to say that's always the case because you might have one where integrating with respect to y because of the y-axis is actually really straightforward, and integrating with respect to x would require an integration technique that either we don't have or is just beyond the scope of this course or whatever. But there you go. That's the entire thing worked out twice, and you see that we do get the same thing. And in this case, it doesn't really matter which differential we chose to work with. It's just one was a lot easier than the other in this case.